Hello everybody. Today we're going to look a little bit more at an electrochemical cell. We're going to learn how to draw them and label the different parts. We're going to learn how to show which direction the electrons and ions are flowing. We're going to figure out which part of the cell gains and loses mass. We're going to look at all those parts of the cell today. So here's an example of a cell. You can see in this example we have the anode on the left and the cathode on the right. Technically, you could draw them any direction you want. This is just the direction I chose. You can see that we have one electrode here and one here. They're pieces of metal. We have manganese here and we have nickel over here. They're connected by these little alligator clips and a wire. We have a solution in each beaker. This one has 1 molar manganese ions, and this one has 1 molar nickel ions. It's important that it's 1 molar because that means it's a standard cell. Remember, the concentration matters. You're going to notice that we've connected them by something called a salt bridge. We'll talk about that in a little bit. This picture has also labeled which direction the electrons are going. And we've labeled the anode with a negative sign and the cathode with a positive sign. These are all things that you would want to include if you were asked to label and draw a cell. So here you can see we designate the anode as a minus. This is the side that is losing those electrons. They are flowing towards the cathode. They go through that wire into the cathode, and we label the cathode with a positive sign. That's where the electrons are being gained, and they're coming from the anode. I think talking to yourself out loud and saying it verbally and describing what's happening early on in your practice problems is very helpful. Here's another example. You can see all the same kind of things are labeled. This time you may see an addition of something like a light bulb showing that electricity is flowing. The light bulb would turn on as the electrons flow through the wires. In this example, they've actually told you what type of salt is in your salt bridge. They told you the equations that are happening on each side. And what I love about this picture is that if we zoom in, they've given us an actual atomic view of what's happening, and I think that's incredibly helpful. Let's look at the anode side first. When this is running, as the cell runs, this side is being oxidized, isn't it? Which means this solid piece of zinc in this example, this strip of metal here, is going to start losing electrons. And as the solid loses electrons, look what happens. The ions are aqueous, which means as this is running, this anode starts getting smaller and smaller. We start losing mass because the neutral metal turns into these aqueous ions that start floating around in our beaker. Compare that to the cathode side. Look over here. Here's a solid strip of neutral copper. The ions that are in the solution here, that are in my beaker, start gaining electrons. And when they gain electrons, they become neutral. They become a solid, and they start plating on to this solid chunk here. So this starts gaining mass. It'll get bigger and bigger. let's look at the salt bridge for a minute and let's think about what's happening there. If we are losing electrons and making all these cations, over time a charge would build up. That's not ideal. That's not what we want. We want to keep that balance, that charge balanced. So the salt bridge allows these negatively charged anions to come into the anode solution to balance out the missing electrons. That way we don't just get a whole beaker filled with cations. We would end up with it being nice and balanced. And on this side, we're losing cations, aren't we? They're becoming neutral. So the potassium is going to flow into this beaker to help balance out all those cations that are being lost as they turn into solid copper. So one of the things you can also do is label which direction your ions are flowing in your salt bridge. If you don't allow those ions to flow, your cell can go dead and stop working. One of the ways to remember which is losing mass and which is gaining mass is this really silly picture. I just love this. Look at this silly thing. An ox, right? That's our anode. And our red cat, that's our cathode. Oxidation is happening here. We are losing electrons. The cathode is gaining the electrons. So what we say is that a red cat gains whatever an ox loses. So if the ox loses its electrons, the red cat, the cathode, is going to gain them. If the ox is losing mass, the red cat is going to gain the mass. So when you see this giant ox crammed into one side, and this skinny, scrawny little kitty on the other side, that can help you remember which one needs to gain some mass. And we can see that the anions need to go over here because we need to replenish the electrons charge that's being lost over there. So hopefully that is weird enough to be memorable. You can see this chapter has so many mnemonics. Maybe make little flashcards or draw your own silly little pictures. Whatever you need to keep these definitions and terms straight in your brain. Okay. So here's what we're talking about with that salt bridge. As those cations form, we got to balance them out with those anions. If you don't know what your salt bridge is, you can just be generic and say anions. And over here, you can say cations. It doesn't matter. If they ask you to sketch a cell, make sure you have something indicating the purpose of that salt bridge. You may hear them talk about completing the circuit or maintaining a charge balance. That's what we're talking about. Without this ability to balance those charges, this wouldn't work. All right, so I'm just going to put up all the various things that we've kind of talked about for these two different locations in the cell, where we have our anode, we have our cathode, talking about which process is occurring, oxidation or reduction, what that means in terms of the electrons, talking about the salt bridge, which direction the various cations are going. Now, this next part we have not gotten to yet. We'll get there in a second. We are going to learn that there's two types of cells. There's electrolytic and there's galvanic. Okay, so an electrolytic cell is one that you have to hook up to a current to drive the reaction. So here you can see that we're going to connect the anode to the positive end of a battery. And down here, we're going to connect the negative end to the cathode. And like we talked about on the previous slides, right, about which side gains and which side loses, when you're trying to electroplate something, when you're trying to cover it in a metal, that's going to happen at the cathode because that's where the mass is being gained. Remember, the red cat needs to gain some weight. Okay. So let's look at these two terms, galvanic versus electrolytic. A galvanic cell is taking chemical energy and turning it into electrical energy. That's going to occur when the cell potential is a positive value. When your cell potential is positive, your Gibbs is negative. It's spontaneous. We're right back to thermodynamics, aren't we? This is something that's real important to remember because this allows you to make connections between electrochem questions and thermodynamic questions. In a galvanic cell, we say that the anode is negative, and we say that the cathode is positive. Remember, this is where the electrons are leaving, and this is where they're going. The electrons are coming from the chemical being oxidized, and they go from that anode into that cathode. An electrolytic cell is a little different because what we're doing is we're using an electrical energy to drive the chemical one, right? We're going from electrical to chemical energy. This is going to happen when your cell potential is negative. When your cell potential is negative, that is not a spontaneous process. It's not doing what it wants to be doing. Your Gibbs is positive, not spontaneous. That's why you have to plug it into an outlet, right? That's why you have to attach it to a battery. That's why you have to give it energy. You have to hook it up to the electricity. Another thing that's a little different is that the anode is now going to be positive and the cathode is negative. The electrons are coming from an external source. And they're going to come in the cathode and they're going to go out the anode. They're going the opposite direction, which is why you see we flip the signs here. You're forcing it to do something that it would not want to do on its own. So I have a couple examples. Here's a galvanic example. We're going to have a zinc and copper. So one of our electrodes is zinc, one of them is copper. I look at my reduction chart and I find these values. So now I need to stop and figure out which one of these equations needs to be reversed. One of them is going to be losing electrons, oxidized. One is going to be gaining electrons, reduced. Which of these has a more positive value? Do you see how the copper has a more positive value? That means that's the one that is more likely to be reduced. It has a tendency to be reduced better. The zinc one, that negative is telling you it does not want to be reduced, does it? It would much rather be oxidized compared to the copper. So that's the one that will be our oxidation step. We're going to have to flip this reaction and we're going to have to flip the sign. Like that. Now I add my reactions together. We see that the zinc is losing electrons. It's going to lose some mass. This is the anode. The copper is gaining the electrons. The red cat reduction, the red cat needs to gain. It's going to gain those electrons and we're going to get a larger mass of copper being produced. When you add these values up, do you see that you get a positive? That means this is galvanic. This is spontaneous. Delta G is negative. It's going to happen all by itself. I do not have to hook this up to electricity to force it to happen. Now let's look at an electrolytic example. We are told that our cell is going to be sodium chloride breaking apart. That's what our cell is going to be doing. They tell you that part. Here's the thing. The equation is telling you that you're going from an ion of sodium to neutral sodium metal, which means it's being reduced, doesn't it? But look at that value in your reduction chart. That's not favorable, is it? It doesn't want to do that. But we're forcing it to do that. We have to look at the equation that they told us about. They are telling us this is happening against its will, okay? It would much rather not, but it's going to. So we need to follow that and make sure that the work we do reflects the actual reaction that's taking place. Not what it would like to do, what it's actually doing. And if you look here, our chloride ion is being oxidized. But look what a positive number that is. It would really rather be reduced. Doesn't matter. It doesn't get to do what it wants. We're forcing it to do something that we want, okay? So we are being told that the sodium ion is reduced, and we are being told that the chloride ion is being oxidized. So I'm going to have to flip this equation here, even though that doesn't feel very good, does it? And what happens to our cell potential? Look at that. That's horrible, isn't it? -4? That is not something that wants to occur. That is not spontaneous. A negative cell potential gets us a positive Gibbs. That's bad. That means this is an electrolytic cell, that it is only going to happen if we force it to happen. We have to plug it in. If you want to know what type of cell you have, you got to calculate your cell potential here and look at the sign. Okay? So that's the big deal. Figuring out what type of cell you have. I'm going to show you one last thing for this, which is called cell notation or line notation. It doesn't get used very often, but I think it's really helpful. It can really simplify things. It's a shorthand, okay? The way it works is you're going to write which substance is the electrode, and then you're going to put a line. You say what the electrolyte solution is in the beaker, and then you put 2 lines. The other side, you put the electrolyte, and then a line, and then the other electrode. We put the oxidation first. You got to lose the electrons first, and then something else can gain them. The single line is just representing what we call a phase barrier. Like you have a solid electrode inside your aqueous electrolyte. Sometimes they may be different, or they may be the same phase. If they're all electrolytes, if you have lots of things in the same phase, then you would use a comma instead. Sometimes we use what's called an inert electrode. That would mean it's not going to actually react, right? Inert means it doesn't react. Sometimes they may tell you the concentrations of your electrolytes because that's important, right? If it's not 1 molar, we need to know that. And this double line represents our salt bridge. That's what's separating the 2 half reactions from each other, right? So what this might look like would be this. We have zinc metal on one side, we have copper metal on the other. We have zinc ions floating around and copper ions floating around. This is the anode. This is the electrolyte solution that the anode is in. The salt bridge separates them. Sometimes you may see it's not actually a salt bridge in a traditional sense. Sometimes we use what's called a porous partition, which is a special material that lets ions go in certain directions, but it functions basically the same. You can see here, right, your anion is still going over here to the anode, and your cations are still going across into the other side. This is the solution that the cathode is in, and this is the copper metal, which is the cathode material. Okay. So I know that was a lot, but I'm hoping that seeing the pictures was helpful. I think seeing pictures of these cells various ways is really helpful to visualize what's happening. Going back to that atomic view, let me go back. This one, right, where you can see what's happening on an atomic level, I think that's really helpful. I think this one is really silly, but can be one of the best mnemonics to remember. Helps you not get things backwards. Okay. So now you know how to use your cell potentials, right? To decide whether something's spontaneous or not. You'll be able to figure out if your cell needs to be hooked up to an outside electrical source or not, right? Is it galvanic versus electrolytic? You'll be able to remember which electrode gains mass and loses mass. You'll know which way the ions are going. You'll be able to do a lot of stuff with our electrochemical cells at this point. Okay? I hope that was helpful. Bye, everybody.